So this next example is going to involve energy and force and work. So this one we're going to be sliding down a slide, assuming that there's no friction, and find our speed at the bottom. And then assuming there is friction, knowing the speed we reach at the bottom, what is the force of the friction? So let's start off here with part A. If no friction is present, what will be his speed at the bottom? So I have this little diagram. Here's our guy, 25 kilograms. He's just a young guy. And he's sliding down this big slide. Sliding down. And at the bottom here, he's going to have a certain speed. So if there's no friction on this slide, which obviously is not the case, but when we're doing this problem in just an intro to physics, we can assume that there's no friction because that makes our calculations so much easier. So if no friction is present, what will be the speed at the bottom? Now the rule that we're going to use here is that the energy at the start is equal to the energy at the end. So his energy that this young guy holds at the start will be equal to the energy at the end. So that is the conservation of energy. So let's write that like this. Energy total 1 is equal to energy total 2. So the energy at the start is equal to the energy at the end. Now what energy do we have at the beginning? This is our beginning, the 1, that's our beginning, and then 2 is when at the end when we reach the bottom of the slide. So what kind of energy do we have at the top here? Well, we're not moving, we have no speed, so there's no kinetic energy, but we have a certain height. So we have a potential energy built up. So at the beginning we have just a potential energy, or the energy of, we call it EG for gravity, because it's the energy that gravity, the potential energy that gravity has to act on our 25 kilogram person. So he's got potential energy, and at the end, all of that potential energy, once he reaches a height of 0, here the height is 0, all of that energy has to go somewhere. And where does it go? Well, it gets converted into speed. So as he comes down this slide, his energy is slowly getting converted from potential gravitational energy to speed, till at the bottom he's got no more potential energy and it's all speed. So we can write that like this. So at the end, it's going to be kinetic energy. That's the energy related to movement. So it's going to involve his speed. So energy potential is equal to energy kinetic at the end. So what's this? Well, our formula for the gravitational energy is mgh. And I'm going to add a subscript 1 for the h because that is his initial height. So he has an initial height up here of 16 meters that we'll be plugging in later. And that is equal to, well, for kinetic energy, what's our formula? Well, it's 1/2 mv squared. And I'm going to add a subscript 2 on this v, so we know it's the velocity at the end, kind of at the bottom of the slide. So let's plug in some values. So our mass, we remember from the question, is 26 kilograms. It's 26 kilograms. G is 9.81 meters per second squared. That's a gravitational constant. Then our h, that's our height. H1 is our starting height, the initial height of the kid. So here it's 16 meters. That's the potential energy. This is the potential energy that we start with. And in the end, it all gets converted to kinetic energy. So our mass, again, will stay the same. It's going to stay 26 kilograms. His mass is not changing. From when our kid is at the top of the slide, up here to when he's at the bottom, he's got the same mass. So that mass, oh, and I just realized wrote this as 25 up here. This should be 26 kilograms. Right, and I'm going to redraw this box as well. So that should be 26 kilograms, my apologies. And then this V2 squared. So that's our unknown value. This is our value that's our unknown. I'm going to make this in green so we can keep track of it. V2. That's our unknown speed at the end. So let's simplify these terms here. Let's start multiplying some things out. So when we multiply this all together, we get a value of 4,080.96. And the units here, kilogram meter per second squared. That's our kilogram meter per second squared. And then another meter. So let's add another meter to that. Is equal to 13 units kilograms V2 squared. All right, now our next step, what we're going to have to do is isolate for this unknown. So our next step is to isolate for V2. That's our unknown. So I'm just gonna rewrite this equation up top. So 4,080.96, and for this I'm gonna fix up these units. So kilogram, meters, these we got 2 meters, so that will become meters squared per second squared. All right, so kilogram meters squared per second squared is equal to 13 kilogram V2 squared. And now I want to bring this 13 kilograms to the other side so we can start isolating V2. So bringing this to the other side as a division, we'll divide it. Dividing by 13 kilograms is equal to V2 squared. So this term we put into our calculator, we get 313.92 meters squared per second squared. As you can see, these kilograms cancel out, so we're left with meters squared per second squared equal to V2 squared. And now we're going to take the square root of both sides. And we will get a value for V2. V2 is equal to 17.717787 meters per second. So looking at our original question, we are given these values with just 2 significant digits. So in our final answer here, we got to round this to 2 significant digits. So I'm going to write that the V2 is equal to 18 meters per second. That's 2 significant digits. And to write a little statement along with that, so V2 is equal to 18 meters per second. What does that mean? Well, that means when our kid reaches the bottom of the slide, once his height is 0, he's going to have a speed of 18 meters per second. That's all his potential energy converted into kinetic energy. So therefore, the kid will have a speed of 18 meters per second at the bottom of the slide. And that's all for part A. Now moving on to part B. If friction is present and he reaches the bottom at a speed of 8.5 meters per second, calculate what the frictional force is. So this is kind of an interesting problem because here we calculated, well, if there's no friction, we're going to have this speed. If there is friction, our speed is going to be 8.5 meters per second, which is significantly less. And we want to know what frictional force would result in a final speed of 8.5 meters per second. So the way we're going to calculate this is first calculate that if it were frictionless, energy at the bottom. So what would be the energy of the kid at the bottom of the slide if it were frictionless? So that's going to be using this speed. And then we're going to calculate the actual energy at the bottom. So that's going to be the actual energy at the bottom using this speed here. And then that will answer, when we subtract the two, we'll be able to answer the question of how much energy was lost due to friction. How much energy was lost due to friction? And then once we know how much energy was lost due to friction, we'll be able to calculate the frictional force. So let's walk through this together. So we calculated that if there was no friction, we would have a speed, this speed here, I'm going to use actually, at the bottom. So if we're frictionless, how much energy will our kid have at the bottom? Well, it's going to be all kinetic. So it's going to be all kinetic. All kinetic energy. Okay, so what's his kinetic energy at the bottom? Well, it's 1/2 mv squared. So 1/2, and his mass is 26 kilograms. And what's his speed at the bottom if there's no friction? Well, that's the value we found here. And I'm going to use this one as opposed to our rounded version just because we want to have a number that is more accurate. And this is technically more accurate, so we're going to be using it for our calculations going forward. So that speed was 17.717787 meters per second, and that's squared. So our EK, all we have to do is plug this into our calculator. Our EK is 4,895.969, and the unit's kilogram meters squared per second squared. And this is joules. So that's an energy. That's good. We have for our energy, we have the right units. Okay, so that is our energy at the bottom of the slide. It's all kinetic if it were friction. Now let's calculate what's the actual energy that the kid has at the bottom given his actual speed. So EK is equal to 1/2 mv squared. Now here we're going to be plugging in the same weight. He's still 26 kilograms, but his velocity is 8.5 meters per second, and that is squared. So let's calculate this. This is his actual kinetic energy. going to be 939.25 kilogram meters squared per second squared. And again, this is joules. Okay, so we have two kinetic energies. One is like a theoretical energy and one is an actual energy. So there's a difference between these two energies. What we actually have and what we would have if there was no friction. So that tells us that because of friction, we lost a certain amount of energy. And to find out what that energy was, we're just going to subtract our two numbers. So our 4,080.95969 joules, that was our energy theoretical, minus our 939.25 joules, that's our actual, gives us a number of 3,141.70696 joules. Well, what does that tell us? We lost this much energy to friction. So we lost 3,141.7 joules to friction. So we lost 3,141 joules to friction. But that's not quite what the question was asking for. We're looking for the frictional force. And how can we go from an energy to a force? Well, we have this formula here that force is equal to work over distance. So we want to know, so we lost this much energy to friction, but over what distance? But over what distance? Okay, so from this, we know that we lost a certain amount of energy to friction over a certain distance. That means that work was done. Force times the distance is equal to work. So some amount of work was done. So that's 3,041.71 joules of work was done by friction. So using this formula, bringing that up here, it's the same formula, just written in terms of F instead of in terms of W. So the force of friction is equal to the work done by friction over the distance that the friction was acting for. So let's start plugging in some variables. So this force of friction, that's our unknown. That's what we're trying to find to solve this question. So force of friction, I'm going to do that in green. So force of friction is equal to the work done by friction. So this is the work done by friction, this value that we found here. So 3,141.70969, and the units were joules, but I'm going to write it now as kilogram meters squared per second squared. And then the distance for which that this friction acted for is going to be this distance here. So we have the friction. The friction is acting counter to the movement. So remember our block, or rather our person, is sliding down with a motion in this direction, and the friction is acting in the opposite direction. Just gonna write friction. So what distance is this friction acting? Like, how long is it acting for? Well, it says 25 meters. So as long as we go from the beginning of the slide to the end of the slide, the friction will be acting, and the distance there is 25 meters. So the distance is 25 meters. So we have some units that'll cancel out. This meters and one of our meters on the top, so we cancel out that exponent. That means the force of friction is equal to, and we just have to type this in our calculator, 125.66839 kilogram meters per second squared. And if you have different decimal points, that's okay. There could be some rounding errors, but what matters is really the first three digits, because we're going to have our answer here in three significant digits. So that tells us the force of friction is equal to 126 newtons, because we're going to round up this 5 because of the 6. We're just going to round up. So 126 newtons. So that tells us that friction is equal to 126 newtons. So that 126 Newton frictional force, that's where our energy went. Because look at, we have this energy at the beginning. Remember, energy at the start. We have this certain amount of energy at the start. That is real. That is real energy that we have. And in our first example, there was no friction, so all of that energy got converted into kinetic energy, and all we had to do was solve for velocity. So as you can see, when there was no friction, our energy at the bottom was exactly the same as our energy at the top. Now, when we introduced friction, it almost appeared as though, oh wait, we actually lost some energy. And although you did lose some speed, there was actually no energy destroyed. So energy cannot be destroyed. So that energy had to go somewhere. And that energy that we were kind of missing from this equation here, the energy that was missing, where did that go? Well, that went into friction. And friction can come out in the form of heat, and also the loss of speed. So heat is produced by friction, so that is where the energy went. The energy did not just disappear, it just went into friction and heat rather than speed. And the friction force was 126 newtons. So we know that 3,142 joules of work was done by friction over 25 meters. Therefore, the force of friction was 126 newtons. And that is the end of this problem.